So what we're going to talk about today is a couple of different things. And to start off with, we have to go over this concept of pressure. Now, if you've ever gone to the doctor's office, they take a blood pressure. I had a group back there talking about the water pressure. Yep, liquids have a pressure as well. Particle movement causing a force against the sides of a container. But typically, pressure is dealing more with gases. Heck, if you watch the weather on the news, they'll talk about a high pressure front moving in or a low pressure front. So when we refer to air pressure, we're referring to the molecule movement, those gases colliding with each other and other things. Because when you have matter present, it is constantly in motion. Gases in particular spread out more, move around more. Now, the difference between that and a liquid, however, is gases are so spread out that even if they are hitting you right now in the face, because there's pressure being applied everywhere, it's so spread out it's really not affecting you. You were born into this pressure, so it doesn't seem abnormal that this is happening right now. Now, I might be going a little out of order with the guided note sheet, because I believe my next slide is partially this way because of we have to share the equipment I'm going to show you a demonstration with here in a minute. I heard at least one or two groups mention the term vacuum when I was walking around. Now, we did not create a vacuum any way, shape, or form in what we just did. However, a vacuum, and this is on your note sheet about halfway down, is referred to a space that's empty of matter. And that includes gases. So again, there's a lot of gas in this room right now, the air that we breathe in. A vacuum would be perfectly void of any matter. However, this is kind of unrealistic. How do you get rid of every last gas molecule in any scenario? It's very difficult to do. So typically what we will refer to as a vacuum is there is significantly less pressure than normal pressure. Again, we've gotten rid of as much as we can. The best example of a vacuum would be outer space. Again, you leave our Earth's atmosphere, and now you are in very close to a vacuum situation. Because there isn't gas molecules just floating around in the cosmos. Gravity will bring them together, and that's how planets and stars form. So it's not a matter of there's just stray things here or there for the most part. Besides just, again, that in our real world we can't have this scenario, outer space is the closest thing to it. We can experimentally, however, show what a vacuum is and how it works. Again, you think of a vacuum as in a vacuum cleaner. Well, that is using differences in air pressure to remove the dirt from the carpeting. We're going to do a few demonstrations with the vacuum pump right now to show you, again, that idea of pressure. So again, on your note sheet where it says normal or standard pressure, that would be either the unit of atmospheres, which is ATM, or millimeters of mercury. Notice the millimeters is your metric conversion. Hg is the element for mercury. And then I believe the other thing on your note sheet, what happens to pressure as you increase altitude? High altitudes have lower pressure. So let's talk about both these things for a little bit. First off, you see a picture on the right-hand side of my slide. It may seem unusual of why are we using millimeters, a distance measurement, in order to measure pressure, how much push something has on something else. What they did for an early barometer is they took a tub full of mercury and a glass tube inverted with mercury. Again, on the weather report, when they say there's a high pressure front, that means that the air is supplying more pressure, more push. So the air would push down on this tub. And the only place the liquid mercury could go then is up the tube.
they would measure the distance up the tube that the mercury would go. And that measurement in distance is what our first pressure measurement was based upon. So a low pressure front moves in, there's a lower amount of pressure pushing down, forcing this up. So then it's a smaller distance. Since then, the unit atmosphere has often been used. I say this can be used as a conversion because 1 atmosphere is 760 millimeters of mercury. I believe there's going to be at least one question on your homework tonight that's going to require you to convert between the two. We did talk on the unit test, however, we are not going to include that on the unit test. Higher altitudes have lower pressure. Denver, Colorado, the Mile High City, for example. Air is a little thinner up there, they would say. And as it's thinner air up there, the air supplies less pressure on things. This is important for a couple of things. First off, cooking directions. When cooking things, they have different directions sometimes for high altitude versus low altitude, because the air pressure will affect that. Secondly, I being a track coach, I'm a little bit more familiar with this, that world-class athletes will typically train at higher altitudes. Lower air pressure means when they're breathing in a little less oxygen, or at least the partial pressure of oxygen is less. So then when they come down to a lower elevation, they're breathing in more, their body can do more than what it's used to doing. It's kind of like when swimmers will swim with, some swimmers say they don't shave their legs until the end of the year to have more resistance as they swim along. But at the end of the year when it counts, they will, so they have less resistance. Again, high altitude training is train your body to work with less oxygen and then go down lower where there is more during your races, and you should have better performance. Okay, next thing that isn't on your note sheet that I want to talk about is, again, a visualization of this idea of how air pressure can do a lot. I mentioned before when I tried to remove the jar from the platform that air was stronger than me. So I gave you the date of 2010, and maybe I'll hit the lights here so you can see these pictures a little bit better. So we are getting close to 9 years ago. I used to live in Sun Prairie before I moved to Wanakee. 9 years ago, 2 doors down from me, their house exploded. Again, when you think of Sun Prairie explosion, you think of the more recent one on their main street. This happened a few years before that. So this picture was taken from my backyard, like you're at my house right now. You can see the screened-in porch of my neighbors, and then next to them you see rubble. So that was the house that actually exploded. Again, the explosion was due to a gas leak, and then a pilot light triggered that gas. Gas lit on fire when it builds up enough, causes the explosion. Now what an explosion really is that air gaining a lot of energy and then pushing forward. So when debris shoots out, that debris is shooting out because air is pushing it out. Now this is the front of my old house, so there's shards of things laying around. I like to show this picture on the bottom because I like to keep things clean, but after that explosion happened, there's a line of blah on my sink because my entire house shook when this happened. Again, people ask me, what was it like? Well, I was sleeping. It was like 3 in the morning when this happened. So all of a sudden, the loudest sound I've ever heard in my life happens. This is the side view of my garage. I don't know if you can see this, but the part that's called the soffit is all mangled. There's a reason why it's mangled. Also, you can tell my window was blown in. Again, that wasn't shrapnel or anything that hit my window. That was air that broke through into my window. So air was able to break the glass. And what happened is when air shot in here, it built up high pressure. A lot of gas molecules came in here, came in here, came in here. They're flooding in because the explosion, the direction of the explosion was towards my house. But at some point, just like with the syringes, when you build up high pressure inside of a container, balance has to occur. And to balance, what happened is this entire garage wall popped out. That's why all the soffits here are all mangled at that point. The only thing that stopped my wall from popping off this concrete slab was my own gas meter. which is kind of scary because the gas meter, if that broke, then my house would have had a gas leak and could have had an issue as well. If you look at the inside view, come on. I recently, when this happened, remodeled our basement where it had fake wood paneling in the basement. What I did is I took that fake wood paneling and I painted it white and I put it in my garage to have some sort of wall on it. And since it was just my garage, I was a little sloppy with the painting. So in particular, probably McCurdy can see I have a line of white paint and then the wall. When that air pressure built up inside my garage, just like when you pushed in on the syringe and built up pressure, pressure had to release. It pushed my garage wall out. So air was what pushed that out. I had to hire somebody to fix that because you can't leave your wall popped out, almost falling off the concrete slab. So he brought in like a forklift and everything and just tried to push it in. It wouldn't budge. So not only am I not stronger than air, his machinery was not stronger than air. What he had to do was he had to jack up the roof, which by the roof was that far lifted off the frame as well because he could see that much space of nails. He had to jack this up and then he could push it back in because even his equipment wasn't powerful enough to do that. We don't see gases. They're too spread out. They're not dense. However, they do a significant amount of work. Again, especially when they are pressurized. Now, this leads us to the ending of our notes here where it says, what is Boyles Law on your sheet? I'm going to give you kind of the definition, and then hopefully you have a little bit of room because I'm going to give you an equation as well. Boyles Law is dealing with how pressure and volume are inversely related. That's a term that we brought up very early in this year. Inversely related means one thing goes up, the other thing goes down. Think about the syringes. When you pushed in on the syringe, you were creating a smaller volume. Inside that syringe then was a higher pressure because it's inversely related. Now, Boyles Law occurs when temperature remains constant. And when you were dealing with the syringes, there was no real change in temperature for us to worry about as well. So again, as volume goes up, pressure goes down, or vice versa. The reason why, if you increase the volume, think about the syringe pulling out the plunger. If you increase the volume, the molecules aren't colliding as often. They're not as close together. They're more spread out. And if they're more spread out, they can't bump into things as often to supply that pressure. This is the mathematical equation we have to be aware of today. P1 V1 equals P2 V2, where the 1's refer to the initial conditions. The 2's refer to the final conditions. Pressure is given to you in either millimeters of mercury or atmospheres, the two most common units for pressure. Volume could be liters or milliliters. What I would like to do to wrap up class is, and actually this note sheet we're going to come back to next time because there's a little bit more notes that I want to do. You did pick up on the way in a sheet that was titled Boyles Law Practice Sheet. I'd like to very quickly go over just either one or two problems dealing with that. For example, number 1, let's perform a conversion other than a metric conversion. Number 1 says how many atmospheres is 337 millimeters of mercury? Just like any type of conversion, metric or other, write down what you're given. So again, we're doing number 1 on this practice sheet right now. But unlike metric conversions, which again, some of you can do in your head, this is a new type of conversion. However, the rules for setting up a conversion remain the same. Whatever you want to solve for goes on the top. In this case, it's atmospheres, ATM. On the bottom is what you have, millimeters of mercury. And now fill in the numbers that relate the two. And remember, standard pressure is 1 atmosphere or 760 millimeters of mercury. Which means I would do division. And I would get 0.443 atmospheres. That's my answer to that first question. Now I'm going to skip number 2 and try to do number 3 fairly quick on here to wrap up class, so you have a couple examples prior to me handing out the homework, the last homework for this unit. Number 3 says, if a flexible container has an initial volume of 237 milliliters at 732 millimeters of mercury, what will the final volume be if the new pressure was decreased to 550? Hopefully you noticed in the question, it said, what will the final volume be? In other words, we want to solve for V2. The only tricky part about these types of problems is we give you 3 of the 4 variables, know what each variable is. For example, the initial volume was 237. The initial pressure was 732. I can multiply those down. The final pressure was 550. And then V2 is my one variable that I'm going to solve for. If I multiply these and divide by 550, I would get 315 milliliters. Which, if you think about it, the pressure in this problem decreased, the volume increased. Inverse relationship. By the way, the math department often with problems like this would suggest isolating the variable before you plug in. In other words, V2 would equal P1 V1 over P2. Divide both sides by P2. And then plug in your numbers and solve. I will accept either way of plugging in right away and solving, or isolating the variable, plugging in and solving. Both should get you to the correct answer if you do it properly.